Okay, so you guys really threw us a curveball with this deep dive request.
Yeah.
Tachyons.
Tachyons.
Faster than light particles.
Right.
It's like something straight out of Star Trek.
Exactly. It's definitely captured the imagination of, well, pretty much anyone who's ever thought about space travel.
Right. Traveling across vast distances in the blink of an eye.
Or maybe even time travel.
Yeah, time travel. That's the big one.
Yeah.
You sent us a ton of research on this, and clearly this idea really, really got you thinking.
Absolutely.
So, I guess the big question is, what are these things? What are tachyons?
So, in the simplest terms, tachyons are hypothetical particles.
Hypothetical. Okay, so we're
in the realm of theory here.
We're the what if.
Exactly. And what if they always travel faster than light?
Always.
Always. Not just a little bit faster, but their very nature is to exist above that cosmic speed limit.
Okay, so that right there already breaks, our fundamental understanding of physics.
Absolutely. Einstein's theory of relativity tells us that nothing can travel faster than light.
Right.
So if tachyons exist, it would really shake things up.
It would really shake things up.
And, it's not just about going fast. It's that they can't slow down to the speed of light or below.
It's like their cosmic rule.
Right, trying to make a fish live on land.
It just doesn't
compute.
Exactly.
So time travel,
yeah.
You brought up the grandfather paradox,
right?
One of the classics.
Classic for a reason, right?
You go back in time, you accidentally prevent your own birth. What happens to reality?
It really messes with the whole cause and effect thing.
Big time.
So how do tachyons fit into this?
Yeah.
Well, some physicists believe that if tachyons could interact with normal matter,
okay,
they could potentially create these things called closed timelike curves.
Closed timelike curves?
Yeah, essentially loops in space-time.
Okay.
Which, in theory, could allow for backward time travel. So tachyons, these faster-than-light particles, could be the key to time travel.
They could be, but of course there's that paradox problem.
Right. Back to the grandfather.
Exactly. It gets very messy very quickly.
Okay, but here's another thing, and I think you had this in your notes.
Yeah.
If these things are zipping around faster than light everywhere, why haven't we seen them?
That's the million-dollar question.
Yeah.
It all comes down to detection.
Okay.
Our current methods for detecting particles are, they're based on things moving slower than light.
So our instruments are...
kind of limited, yeah.
Limited, yeah.
It's like trying to catch a bullet train with a fishing net.
Right. The tools just aren't built for that.
Exactly. The tools just aren't there yet.
Okay, and even if we could detect them, what if they interact with, normal matter so weakly that they just pass through us?
Like cosmic ghosts.
Cosmic ghosts, yeah, I like that.
Right. Some theories suggest that tachyons might only interact with each other, leaving our everyday world untouched.
Okay, so we got this whole other realm
potentially
existing right alongside us.
Yeah, but we're just oblivious to it.
Oblivious, wow.
Isn't that wild?
That's mind-blowing.
Yeah.
But we're getting a little out there.
Okay, yeah, let's reel it back in.
Let's bring it back to the science here.
To the science.
So you mentioned, I think, that tachyons actually fit into some theoretical frameworks.
Yes, they do.
Like actual physics, not just... sci-fi fantasy.
Right. And this is where it gets really interesting because, remember, we haven't actually observed tachyons.
Right.
But they do appear in some models of physics.
So they're mathematically possible.
Exactly. Like, for example, certain versions of string theory.
Right, string theory.
Which, as you know, is already pretty out there.
Yeah, a whole other can of worms.
Exactly. But in some versions of string theory, tachyons emerge as vibrations of these tiny little strings that make up the universe.
So it's like the universe has a built-in loophole for faster-than-light travel.
It kind of seems that way, right?
It kind of seems that way, yeah. And then there's also...
Oh, yeah, and you also have quantum field theory.
Right, quantum field theory, where things get even weirder.
Even weirder.
Because particles can exist in states that, defy our normal understanding of space-time.
Exactly, and in some interpretations of quantum field theory, you can have particles that behave like tachyons.
So, even though we haven't seen them, the math suggests they could be real.
The math is there, yeah.
Okay, so... big question, and I think this is where we leave it for our listeners to ponder. Are tachyons real?
It's the big mystery, isn't it?
It's the big mystery.
And, maybe one day we'll have the technology to actually detect these particles.
That would be something.
It would be revolutionary, right?
But even if we don't ever, physically find them,
yeah,
just thinking about them
pushes
the boundaries of, what we thought we knew about the universe.
Absolutely. It forces us to question our assumptions about reality.
And that's what's so cool about this whole deep dive, right?
I think so.
So to everyone listening, as you continue to, explore this on your own, maybe do your own deep dive.
Yeah.
I want to leave you with this.
Okay.
What if the universe is not just stranger than we imagine, but stranger than we can imagine?
Ooh, that's a good one.
That's where I leave it.
I like that.
Think about it.
I will.
All right. Till next time.